Hi, we're going to go over the answers to the last two problems in this assignment on energy bar charts. We look at scenario 5. The human cannonball is launched from a spring cannon. I don't know if you knew this, but there is no explosion in the cannon. That would kill the person. So they have some kind of spring-like mechanism. Okay, maybe it's pneumatic in real life, but we're going to call it a big spring has been compressed. The cannonball is sitting on top of that on a platform or something that gets pushed by the spring, gets launched, goes up to some high point, still moving though, comes down at D about the same height as it was at B, and then it lands into the net, which we're conveniently saying is back at the initial low point level. And then we could have said there's some elastic energy there, but I'm just going to say that it's all dissipated, that it's all going to be dissipated. So the net is a little bit warmer, he's a little warmer, the air is a little warmer, and that's how we're going to approach the problem. Okay, so let's see. At position A, the human is in the barrel of the cannon at ground level, and the spring in the cannon is compressed. So that's the key. We don't have to do work on the spring to give it energy. It's already in the system. So let's look at A, and we see that all of the energy is elastic. Okay, now, when he's launched, so what we're treating as is the human, the cannon, the spring are all part of this system. So we're not saying that the spring is going to do work. We could have in a different, but we're going to say that the spring and the cannon and the human are all part of one system. So that elastic potential energy that was in there at A is gone from the spring. So there's no more energy. So we have to say, well, where did it go? Well, we see that the human cannonball is a little bit, he's elevated, not quite at the high point, but he's on his way. So he's gained some gravitational potential energy from where he was at A. So I'm going to give him one block. You could have said two if you want. Maybe now that I look at it, maybe it would be two. But there's some amount that's gone to gravitational potential energy. The number of blocks are not as important as keeping the total blocks accounted for and seeing how they transition. Okay, so now we're going to say, well, where's the other three blocks? Kinetic energy. Now he's going to go up in the air, getting higher and higher until he's at a high point. But we notice that he's still moving. So I'm going to say 3 blocks of gravitational and 1 block of kinetic. I could easily see now that it could have been 2 and 2. And again, the numbers aren't so important as the transformation and the accountability of the blocks are all the same. Okay, at D, I'm thinking he's about the same level as he was when he at B. So I'm going to say that D should look exactly like B. And that would be a key point. That is, if you believe B and D are at the same level, your energy chart for B should be the same as D. Okay, and again at E, we're going to include the net as part of our system, so no work. And what we're saying is everything, all that energy that used to be in the spring and became partly kinetic, partly gravitational, is now just gone to heat. Basically, things got a little bit warmer, and now that energy is dissipating. Scenario 6. We have a roller coaster car at A on the ground level and not moving. It is then lifted up to B by who knows what. A cable, some kind of lifting device, but it seems to be work is done raising it up to B. B is not moving, but it's all they do is take the brakes off, and then it comes roaring down, gaining speed. See, it's back at the low point. Heading up to D, it starts to slow down, and it's 2/5 of the way. You can treat it as half and half if you want for our purposes, and that's where our analysis stops. But we know that, of course, it would continue to go, and the fun would end somewhere here off the screen. Okay, so at A, we see our inventory analysis says there's no energy. There's no kinetic, no gravitational potential, and there's nothing spring-like in this scenario. So now we see that as we go from A to B, work is done. Hey, slow down. And again, I'm just kind of arbitrarily picking 4 blocks of work done on the cars. It's raised up to B. So now our energy bar charts better have 4 blocks of energy, and at B it's all gravitational. Now as the car transitions from B down to C, no work is done. And so the energy at C is going to be equal, and now it's back essentially down at the ground level. There's no gravitational potential. Where'd the energy go? You know, all kinetic. Now at D, it begins to climb back up. And so I made it about 1.5 blocks of gravitational potential. And that means we have 2.5 blocks left, and that's going to be all kinetic. Okay, moving on, scenario number 7. Okay, we have a dynamics cart like the one we used in class. It is currently going 4 meters per second at A. It runs into a spring, compresses the spring, and then the spring pushes back, the cart rebounds off, and then we see, though, that it's only going half as fast at C as it was coming in. So this is going slower, and we see here that the spring is warmer. Hint, E-dis. Okay, so at A, and nothing changes height in this scenario, so no gravitational potential energy. Okay, at A, we're showing that that's all kinetic coming in. There's no work, so, oh, that's right, I forgot. We're going to go all the way to the end, because what happens at B is a little bit complicated, and there's a number of ways we could think about showing the energy, what's going on with the energy here. So it's a lot cleaner at the ends. So we looked at A, all kinetic. We looked at C, or we're going to look at C, and then we'll come back and finish B. Okay, now at C, we see that the car is only going half as fast. Now you might think that the kinetic energy is only going to be half, but that would be not correct. You say, how could that not be correct? Because the formula for kinetic energy is 1/2 mv squared. So it turns out that if you're going half as fast as you were before, you only have 1/4 the kinetic energy that you did. Now, for our purposes in this, it's not that important. The main thing is that you see that the kinetic energy has been reduced. That we started out at A with 4, and now we're down to 1. If you put 2, that's fine. But that's fine for now, but eventually you're going to want to see that half as fast as 1/4. Okay, that means where'd that other 3 blocks of energy go? Well, it didn't go into the spring. Well, it did, some of it, but the spring is sprung. There's no energy in the spring. So all that energy, all that missing energy, never gets destroyed. It's somewhere, and here it's going to be E-dis, that the spring has gotten warmer. Who knows, maybe the back of the cart's gotten warmer. I mean, it goes everywhere. Okay, now let's go back to B. Now B, the cart is not moving at B, so we know there's going to be no kinetic energy at B. Okay, gravitational potential energy, forget about it. It's all flat. So that means we have 2 choices left. How much do we want to show as energy in the spring? We should show some, and how much of it is at E-dis at this point? Okay, what I did, I picked a middle ground, and I said basically 2 blocks of E-dis, 2 blocks of elastic potential. And that is the end.